In this video, I want to revisit stoichiometry. We looked at stoichiometry earlier in pre-AP. It was back when we did empirical formulas and molecular formulas, percent compositions, those type of things are classified as compound stoichiometry. And that's when we figure out the ratios of the different atoms that make up a molecule. In this video, I want to focus more on reaction stoichiometry. And these are relationships between the reactants and the product. So let's start kind of back at the beginning, because when we learned compound stoichiometry, we didn't really talk much about the word itself. Stoichiometry was first coined in 1792 by a German by the name of Jeremias Richter. That just gives you an idea about how long this idea has been around. It actually predates modern atomic theory that Dalton came up with in the early 1800s. And the observation that early chemists were making was that there always seemed to be a consistent formula, like a recipe, to make products from chemical reactions. So the word stoichiometry comes from two parts. It comes from the Greek. It's stoichion, and I guess is how you pronounce that, which means element. And then the one you're more familiar with, metry, however you pronounce it, which means to measure in the Greek. So we're talking about measuring the elements. So really, it's just a way to calculate products and also the reactants. You can work it backwards in a chemical reaction. I'll just abbreviate reaction with RXN. Now, what's it based on? Well, it's based on the number of particles, atoms or molecules that you have. So based on the number of molecules or atoms, because sometimes atoms are elemental in the reaction. For example, calcium plus sulfur to make calcium sulfide. Calcium there is an atom that you would keep up with. So we've learned earlier that molecules and atoms, like if you have two molecules or three atoms, you can scale that up using Avogadro's number to really mean moles. So let's go down to this reaction right here, and let me read that for you in a couple of different ways. I could read this reaction in skeleton form to say 2 molecules of hydrochloric acid plus 1 molecule of barium hydroxide yields 1 molecule of barium chloride plus 2 molecules of water. And then we can look at the ratios 2 to 1s, and we'll talk more about that in a second. But if I just scale that up using Avogadro's number, which would apply to each reactant and product, I could also read that reaction this way. 2 moles of hydrochloric acid plus 1 mole of barium hydroxide yields 1 mole of barium chloride plus 2 moles of water. So it all scales up. Stoichiometry is all based on the law of conservation of mass, which is very simple, a little bit oversimplified, as matter can't be created or destroyed. In other words, when you do a chemical reaction, the mass of your reactants, when you're at the beginning, has to equal the mass of everything at the end. And that does not mean that all of your reactants will get converted into products. That can happen. But you could also have a little extra reactant that doesn't get reacted. In the end, you can add up the mass of your products and any extra stuff that you didn't react, and it should equal the mass of what you had at the very beginning. So here's an example, taking the same reaction. If I started out with, I'm just making these up by the way, these numbers are probably not even that accurate. 10 grams plus 25 grams, for example. If at the end of this reaction I measured 20 grams of the barium chloride, and I also examined to make sure I didn't have any extra reactants left over, then I would be able to figure out how much mass of water I would make. If I add these up, 10 plus 25 is 35. So the products have to equal that mass as well, which means I would have made 15 grams of the water. The masses have to equal. So in a chemical reaction, matter is conserved, mass is conserved, but one thing that is not conserved is the number of moles. The number of moles can change because the molecules can break up, and you can actually have some new ratios form, but the mass, importantly, the mass has to stay the same. Let's play with some ratios here and kind of learn how to interpret it or how to use stoichiometry in a chemical equation. Let's take an easy one. Let's just say, okay, I have 1 molecule of barium hydroxide using the ratios given by the coefficients. So you can always determine your ratios by looking at coefficients. So that one's a 1, this one's a 1, this is a 2. For every 1 barium hydroxide that I would react in this reaction, the coefficient here, 2, tells me that I'm going to need 2 HCl's. And then 1 barium hydroxide also tells me that I would make 1 barium chloride. And then 1 barium hydroxide tells me I would make 2 waters. So again, that's using the ratios given by the coefficients. What if that number was 5? Think to yourself, how many HCl's would I have or need to react 5 barium hydroxides? Well, double it, you would need 10. How many barium chlorides would I make from 5 barium hydroxides? Well, it's a 1-to-1 ratio, so you would need 5. And then you would also make 10 waters. Let's try a different reactant. Let's start with 12 moles. Let's just call it moles this time. 12 moles of HCl. How many barium hydroxides would I need? Well, you can see for every 2 you need 1 the barium hydroxide, so you would have half of that. You would need 6. And then you would make 6 barium chlorides and then 12 waters. We can also use stoichiometry with the products. If I knew that I made 4 barium chlorides, how many waters? Well, I make 2 waters for every barium chloride, so I know that I would make 8 waters as well. Now let's work it backwards. How much of the reactants did I need to make 4 barium chlorides? Well, it's a 1-to-1 ratio, so I would need that many barium hydroxides. And I would need twice as many HCl's, so that would be 8. And it would work with the other product as well. If I start with 10, knowing that I made 10 waters, then I would also make 5 barium chlorides. 10 waters mean I had to start with 10 HCl's and 5 barium hydroxides. All right, you try this one. If I start with 20 HCl's, how many of each of the other 3 species would I need? Hit pause if you need a moment to think. All right, let's see how well you did. If I had 20, half of that would be 10. I would make 10 of these and 20 waters. So far, the whole numbers are easy, but what makes this complicated? Well, as you've seen in our mole conversions, we almost never get to use whole numbers. So for example, you can see it starting to kind of get a little squirrely. If I had a 1.25 moles of the BaCl2, now we're starting to deal with decimal numbers, and even though this one's not that hard, the ratio still holds. I still have 2 waters for every 1 barium chloride, so I would still be able to calculate 2.50. And then the ratios still hold. But that just gives you a sneak peek at how the math starts becoming trickier as you add decimals to it. But conceptually, it's always this simple. Now I want to practice with you going through a different chemical equation. I want you to think about these. So after every question we go through, hit pause, think about it. Don't just let me rush you through this, okay? So here we have 3 calcium hydroxides plus 2 phosphoric acids. We're going to yield 6 waters and a singular calcium phosphate. So in part A, what is the ratio of calcium hydroxide to phosphoric acid? I just want to point out that the way this is worded is very important. If it says calcium hydroxide to phosphoric acid, then that's exactly the way you need to express it. And looking at the coefficients, because that's where our ratios come from, this is 3 calcium hydroxides for every 2 phosphoric acids. So it's a 3-to-2 ratio. All right, B, what is the ratio of phosphoric acid to water? Think about that one. Okay, we can see that it's going to be a 2-to-6, and that is a perfectly fine answer. This isn't math. What we're trying to do here does not require us to simplify. I know a lot of you feel that burning desire to simplify, so that would also be an acceptable answer, 1-to-3. Part C, what is the ratio of calcium phosphate to calcium hydroxide? So that's now a product to a reactant. It is 1-to-3. All right, so that's just finding the ratios. These ratios will end up becoming our conversion factors when we do our dimensional analysis part of stoichiometry. Part D, how many moles of calcium hydroxide will be needed to produce 12 moles of water? All right, well, 12 moles of water. And looking at the chemical equation, I know that the ratio is 6 waters for every 3 calcium hydroxides. So if I'm going to produce 12 waters, I'm going to need half of that, or 6 moles of the calcium hydroxide. That's utilizing a, in this case, it would be a 1-to-2 ratio to help you get from 12 to 6. In part E, if I have 6 moles of phosphoric acid, how many moles of calcium hydroxide will I need? So what I'm looking for here now is the ratio of calcium hydroxide to phosphoric acid. So it's a 3-to-2 ratio. Think about what you would do on that one. Okay, so really what you're doing here is you're thinking, okay, if I have 6, and then I'm going to utilize a 3-to-2 ratio, that means that I'm going to need 9 moles of the calcium hydroxide. In part F, if I have produced 3 moles of calcium phosphate, how many of water were also produced? So that's a pretty simple ratio, 3 calcium phosphates. The ratio there is 6-to-1. 6-to-1. So if I have 3, multiply it times 6, divided by 1, that's the 6-to-1 ratio, and I'm going to have 18 moles. In these last 2 problems, I'm going to introduce to you a couple of the more advanced topics in this unit. And in G, we're going to talk about limiting. And then in H, we're going to talk about excess. And we'll revisit both of these topics in separate videos. But this is just, remember, real simple, keeping it real simple. In G, if I have 3 moles of calcium hydroxide and 2 moles of phosphoric acid, I have what are called stoichiometric amounts. That means both reactants are going to be used up completely, and I won't have any leftovers. If, though, on the other hand, I have 5 moles of phosphoric acid and 8 moles of calcium hydroxide, which reactant will run out first? Now, I know that something is going to run out first because 5 and 8 are not able to simplify down to a 3-to-2 ratio. So I am off the ratio. I will have one of the reactants run out first. Can you just real simply think about which one is going to run out first using your ratios? If you think about it real quickly, if I have 5 moles of the phosphoric acid, I would need 7.5 moles of the calcium hydroxide. Do you have 7.5 moles? Yeah, you have 8. So that's not going to run out first. But if I have, for the 8 moles of calcium hydroxide, you're going to need 5.3 moles of the phosphoric acid. Do you have 5.3 moles? Well, obviously not. You only have 5. So the phosphoric acid is going to run out first. And we call that the limiting reactant. That conceptually is very important because that's the one that's going to run out first. It's like the amount of gas in your car. When it runs out, the thing's over. In this case, the reaction is over. And we need to always identify the limiting one first. And we'll get back to that. But in 8, let's talk about the other type of reactant, excess. In 8, 3 moles of calcium hydroxide still require 2 moles of phosphoric acid. So the same ratio holds. If I have 4 moles of phosphoric acid now, and the 8 moles of calcium hydroxide, which reactant is there extra of? So I'm not asking which one runs out first, I'm just asking which one is left over. Well, it's really very similar to part G. Instead of 5, I gave you 4, was still with 8. So we haven't really changed a whole lot. The one that's going to run out first is still the calcium hydroxide. And you can use the ratios to prove that. So that is the excess reactant. How much extra is there? We're going to eventually call that how much excess. Excess means leftover. So using these ratios, knowing that the phosphoric acid is going to be the limiting one in this case, how much of the calcium hydroxide would I need? So here again, we'll start with your 4. For 4 phosphoric acids, how much calcium hydroxide would you need? Well, let's think about it. We are still in a 3:2 ratio, so you're going to need 6 moles. Well, I have 6. I actually have 8. And so the excess would be not what I have, not what I need, but what's left over, in this case the 2 moles. So I bet most of you figured that out in your head. It's not very difficult, but there is some math to it, and we're going to practice that math with some more chemistry type problems moving forward. Let me know if you don't understand this or if you have any questions.